Assalamualaikum warahmatullahi wabarakatuh. We are from Group 4. We'll be presenting for our MAT523 project, uh, least square solutions and best fit curve. Our title is Malaysia COVID-19 Dataset. This is our team members led by Muhammad Fahim Iman bin Mat Saufian, and then Anastafikul Hakim bin Muhammad Rosdi, Muhammad Anif Fikri bin Ahmad Shah, Airil Imran bin Ismail, and myself, Syahrul Haziq bin Salehan. We will begin with the introduction of our dataset. We have taken our data from Kaggle titled Malaysia COVID-19 Dataset. The dataset provides detailed daily records of COVID-19 from early 2020 to 2021. The data includes information such as number of new cases, active cases, recoveries, deaths, and so on. For this project, we have selected data from specific date from 1 June to 10 June of 2021 to analyze the relationship between the number of new COVID-19 cases X and the number of daily deaths Y. This is our dataset consists of date, number of new cases X, and number of deaths Y. The lowest number of new cases is 5,271 and the highest is 8,209. For the number of deaths, minimum is 71 and the highest is 126.
And for the next part, we will be doing the quadratic model. We will be using the quadratic equation, which is y equals to a plus bx plus cx squared. The variable y is the number of deaths, the variable x equals to the number of new cases, and the variable a, b, and c equals to the coefficients of equations. On our right side, you will see that we have inputted the value of y and x into our equation, totaling our equation up to 10 equations. And for the maple calculation, we have inputted the x value, which is the smallest, equals to 5271, and the highest is equals to 8209 for the x value. And for the y value, the lowest is the 71 value, and the highest is at 126. For the a, we have inputted 1111 for all of the 10 values. And for the maple calculation, we want to get the equation of ax equals to b. So on the left side, we will be doing the ax and then x squared. On the right side, we will be doing a combined with y to get the ax equals to b from the equation.
So, as we can see here, I assign the augmented matrix to AY and then I do a reduce row echelon form command on AY so that it will be in RREF. If you look at row 4, there's a contradiction of 0 equals to 1. So, it is proven that the system is inconsistent.
So after we verify our consistency, we can do the normal system. So for the manual calculation, the formula for normal system is A transpose A, X is equal to A transpose B. So we need to find A transpose A and A transpose B. So for normal system on Maple calculation, we already get the A value from before. So we just transpose it in the Maple and then times with A, we will get the answer same as A transpose B.
And now for the type of solution on the manual calculation, we will be getting the determinant. So to get the determinant, we will be using the A transpose A. And we have inputted the numbers into the A transpose A. And as you can see, we have gotten the number. And since A transpose A does not equal to 0, it is a unique solution. And To double make sure, we have compared the answer on the manual calculation with the Apple calculation, and it is the same. Now, for the type of solution on the Maple calculation, we have declared that A equals to determinant ATA, which is A transpose A, and we have gotten the answer, which is, as you can see, now, since A transpose A, or since ATA does not equal to 0, it is a unique solution, and the answer is the same as our manual calculation.
So after we know that the determinant is not equal to 0, so it is a unique solution. So we can do our augmented matrix from A transpose A and A transpose B, and then we calculate it by using row echelon form. So the final answer is we get our C is equal to 4.15134 times 10 negative 6. And then we can find our B and A. After that, we get our quadratic function answer. As our maple calculation, we cannot do the row echelon form, and we need to use reduced row echelon form. And then we have to use eval in order to get the decimal number. If not, it will get a fraction number. And then we get our answer for the quadratic equation.
On this slide, we present the graphical representation of our maple calculation. Using maple, we first define a plot of our function y over the range of x values from 5200 to 8300. This is the command that allows us to visualize both the original data and the fit curve on the same graph. As you can see in the graph on the right, the blue dots represent our data points, while the smooth curve is the result of the function y we plotted. This visual comparison helps us understand how well the function fits the observed data, and we can observe a noticeable upward trend, suggesting a positive relationship between x and y. This graph is crucial in supporting our finding and confirming the accuracy of our maple computation. So for the manual calculation for error vector and magnitude, first we use the error vector formula to calculate the error, and we got the answer at section 2. And for section 3, we calculate error, magnitude error, and the last answer is 40.2264.
This is error vector and magnitude by using maple calculation. The least square error vector equation is equal to b minus ax. First, we find the x from a, b, c from the quadratic function, and then we find the error by y minus a dot ans. Then we find the magnitude of error, and we got 40.22, which means the curve didn't match perfectly, and the total error is around 40 depth spread across all 10 days.
To sum up, the quadratic model gives a good idea of how new COVID-19 case and death are related over the 10 days we study. It shows the general trend, but some results suggest other things might also affect the numbers of deaths. The model works okay, but using better models or more days of data could give us a clearer picture.